Hello, Paul Jackson here. I'm here to talk you through the fetch, decode and execute cycle on a CPU. So to understand the fetch, decode, execute cycle, we have to understand that inside a CPU are high-speed memory devices called registers. And although this is a simplification of what happens in a modern processor, the conceptual view is that we would have registers as follows. We'd have the accumulator, which is a register in the arithmetic logic unit. We have a program counter so that we can keep track of how we go through the instructions that are required to be carried out. We have a current instruction register which examines the instruction and any data within it, which is then operated on. We also have the memory address register, which obviously has a map of every single address in the random access memory, RAM. And we also have the memory data register, which stores the instruction or data that has been retrieved from the memory at whatever address was required. And here's a diagram of how they all fit together. So you notice there on the right hand side the main memory is a crucial part, and that has several connections to some of the different registers. If you're not sure what these acronyms are, then I suggest you just rewind back to the list. So let's see in action how this fetch, decode, execute cycle works. So the first step of the fetch phase is that the memory address of the next instruction to be carried out is copied from this register, the program counter, into the memory address register. Next, the memory address register accesses the main memory at the address that has been given and retrieves from the main memory the instruction, which is then passed to the memory data register. And at the same time, the program counter, which has to keep moving forward with each cycle of the processor, is incremented by 1. This third part of the fetch part of the cycle sees the contents of the memory data register being copied to the current instruction register. And now, with that instruction in the CIR, we come to the end of what we've called the fetch phase. So we've basically retrieved an instruction from an address in main memory. Now it's in the CIR and we're ready to examine it. So we're now on to the decode phase, and there are 3 different things that could happen here. One is that the instruction in the CIR is actually going to refer to another memory address. That's not uncommon, and if that's the case, then that address is then copied over to the memory address register. Now, it might be the case, if we look at this second option, that the instruction in the CIR actually has data with it. So, for example, it might be, the instruction might be put this value 0001 into the accumulator. And so that is an instruction with actual data. If that's the case, then we'd take that data and we would actually copy it into the memory data register, perhaps awaiting the accumulator to do something with it. And most likely, if that is the case, then this third option, which tends to follow from the second option, is that the memory data register would copy something into the accumulator. And now we're coming to the end of the decode phase, and that just leaves us the execute phase. Now, in the CIR, we have what's called an opcode, and an opcode also has an operand. And the opcode is the instruction, and the operand is the thing to be instructed upon. So let's say, for example, that it was, an operation where we add two values together. Well, one value might already be in the accumulator from the previous instruction. And so the instruction in the CIR might be add a number. For example, I said just now, didn't I? Add 0001 to the contents of the accumulator. And let's say that also has 0001 inside it. The accumulator performs simple instructions and comparisons and mathematics, and so perhaps it passes the result to the memory data register of 0002. That needs to be put somewhere, and so it is then likely that the memory data register would then copy that value to an address in the main memory. And that shorter execute phase there is the end of the fetch, decode, execute cycle. And then we go all the way around again to the program counter, passing the next instruction to the memory address register, which is where we started. So let's summarize what we've just looked at. The fetch, decode, execute cycle describes the processes that need to happen once data and instructions have been retrieved from secondary storage. Now that's often the hard drive. And whatever's in the hard drive goes into the random access memory, so a program, for example. And what this cycle does is that it takes those instructions and data in order and examines them and carries out whatever operation is required. The outputs of that go back into the RAM and ultimately will end up again on the secondary storage, usually. Now let's bear in mind also that what we've seen is a conceptual example of the cycle. It's greatly simplified, and you'll find that modern processors will have many more registers inside them. But some simple computer systems may still utilize something almost exactly like what we've seen here. The principles hold good, whatever the situation. And my final point here is just to remember that what we're looking at is data and instructions coming from the random access memory where they've been placed from the secondary storage, and line by line each part of the program being put into the CLI and examined. So the opcode or the instruction and the operand, the data itself, and being moved around, operated on, and the result then put back into the random access memory. It's important because what you write as a programmer will ultimately be compiled down to machine code into an ordered set of instructions. And every time that the clock ticks on the processor, which on a modern processor is likely to be billions of times a second, one of these instructions can be carried out. So that's my summary of the fetch, decode and execute cycle.